let me start with the first part of this presentation. Okay, so this is where we started from. You can see this human evolution timeline, right? So now we started from here. So you see the timeline 4,40,000 years ago. How old do you think our universe is with the current information available? How old you think the universe is with the current information available? How old is the universe? Universe 13.4 something billion years. Very good answer. Okay, maybe 13 point bit more, close to 14 billion. Okay, billion years. 1 billion is 100 crores. Okay, fine. So this is if you see like 440,000 years is pretty small when you talk about 14 billion years. 14 billion is 14 into 100 crore years. That is 1400 crore years. In that, 4,40,000 is like a peanut. And in that 4,40,000, we are just branching out. The Homo sapiens species whom we belong to, we're just branching out. And you see, we talked about the different brothers and sisters of ours, Denisovans and Neanderthals and all. You see, so that is some 25,000, 30,000, 40,000 years back. So which means whatever we have produced, humans, the last 10, 12,000 years, is a very brief part of the world's history. And then in that 10,000 years, what happened is what we try to talk about here. So here we are talking about after the last and fifth ice age, after the fifth climate change, that is around 10, 12,000 years back, is when the civilization which we are talking about built. This is the story of that. Okay, and from there we talked about how the change from the Stone Age man to the New Age man happened. And further, whatever we talked about was like how the scientific thought process developed. Then we started telling about the very fundamental scientific knowledge, which has been very critical. There are a lot of other scientific knowledge which is critical, but this has been pretty critical, that the realization that Earth is spherical, how it came. Then we talked about how philosophers, scientists, thinkers, intellects, they started thinking about how this world is functioning. What is happening in this universe? Who are we? Why did we come here? So it is a mix of philosophy, come science, to animals, to humans, a lot of things. So we traversed through Socrates, Plato, Aristotle, all those things. And you might remember that that time you did not have classrooms like this, which talk by telling physics is a separate subject, history is a separate subject kind of stuff. There were classrooms, there were learning centers, but then it was a bit different. So the whatever science we are talking about, it was like intertwined with the other branches of whatever knowledge streams which we talk about. Okay, so philosophy, science, and everything was mixed. Actually, it is like that. So here in our class, in GrainEd classes, we are trying to bring it back by telling whatever you are trying in separate branches, we are trying to make a meaning out by integrating all those things. Actually, that is how it is. Because the universe does not know that you are learning physics in one class or geography in one another class. It's not bothered about that. The universal phenomenon has nothing to do with our classroom. So all these are assimilated so that it is easy to learn. But then, is it becoming very difficult to comprehend because you are learning it in small pieces? Which is what we are trying to address, one of the goals of this exercise. Then we talked about the Greek civilization, about many scientists, the school of Athens and all. Then we mentioned about the universal understanding, the start of a couple of millenniums back, even till like the 2nd century of AD, the understanding that Earth is the center of the universe and everything else is rotating the Earth. So that was the predominant understanding at that time. Then we talked about further what happened. A lot of contributions from different parts of the world, different scientists. One about many Indian scientists we talked about. And then we mentioned about a guy, a Kerala-based scientist called Madhava. Okay, I don't know how many of you are able to read Malayalam. There's a very famous novel in Malayalam which took headlines recently called Francis Ittikora. Francis Ittikora. In that, this Madhava is coming as one character. It's a very famous novel. Okay, and he's a very famous Kerala-based mathematician, and we had something called Kerala School of Mathematics. And Joseph sir mentioned you about that book. He showed you even the cover of that book, The Crust of the Peacock by Dr. Geo all those things. And then we talked about the Arabian science, the fruitful periods of Islamic civilization, that's from the 8th century to 13th century. Like what were their contribution? Like literally almost every branch of science which we know today were like been invented, were like been prospered during that time. Further, from there, like this is through like till 13th century, we have to understand that Europe was having the so-called dark period at that time. There were not much of green shoots of science and knowledge at that time. It's not like it is like zero, probably at a low pedal. Okay. Then we talked about some specific inventions of some Arabian scientists. And that time we also mentioned that there were some Arabian scientists who proposed that the so-called geocentric model doesn't seem to be right. And they started working on that. But then after the 13th century, the Abbasid Caliphate, that was the end of it, because of the Genghis Khan's invasion and all. And then it slowly came to a decline. So then you start to see the European Renaissance. And that is the time when Copernicus, a priest, who started based on his astronomical data, he proposed as what we call as heliocentric model. Like the sun is the center of the universe. We discussed about the reasons why he talked about that. So this was the artistic impression about this gentleman called Copernicus. Okay. And then we also mentioned about his model. And we told that after Copernicus, although he proposed that model, he did not know why those things are happening. And then we also told that Galileo came and he had his own inventions, which like sort of cemented the concept that yeah, it is a heliocentric universe. Sun is the center of the universe. And further from there, we mentioned about a guy called Tycho Brahe, another scientist, his model. Then in the last class, it was a disrupted class because of some technological glitches. We started talking about a person called Johannes Kepler. I also talked that this Johannes Kepler was a disciple of Tycho Brahe, and that there were allegations that Johannes Kepler killed Tycho Brahe to get the wealth of information he had. And a couple of times, Tycho Brahe's dead body was exhumed and done re-postmortem, which one was like pretty recently, I think around 7-8 years back. And then as it stands today, Johannes Kepler has been exonerated from all those charges. And he's one of the greatest scientists of the world. He proposed 3 laws of planetary science. This is called Kepler Law. The first one was that a law of ellipses. So he mentioned, based on his study of the universe, that all the planets have not a spherical, not a perfect circular orbit, they have an elliptical orbit. And that explains something like why there is, we mentioned the distance between 2 solstices, why that is different. So that explains things like that. And then we mentioned his second law of Kepler, which we tell as law of equal area. But what does that mean? Is when the planets come closer to the sun, they become faster. Their speed increases. When they are away from the sun, they slow down. And you all told it is because of gravity, which is right, rightfully so. But then that was like Newton's contribution later by telling that explaining all the Kepler laws, with even mathematical equation. That was Newton's contribution. Then we told about the third law of Kepler. We were at this last time. So there actually he came up with an important observation, which is giving the relationship between the circumference of an orbit, or maybe we can tell the radius of the orbit. Like from the radius you get the from the radius of the orbit is the distance between sun to that planet. Okay, so the relationship between the distance from sun to a planet and the planet speed of rotation. So we told that is an equation called T square by R cubed is a constant. That means square of the period, that is the time takes for one rotation, ratio of cube of the radius of that orbit is a constant. So that means that the understanding, the meaning of that is when a planet is away from the sun, it is actually traveling at a slower speed. So you see this diagram. The speed of Mercury is 47.87 kilometer per second. Like in 1 second, it travels 47 kilometer. And I think this is something which you all know, that Earth is roughly having a 30 kilometer per second. Per second, you should understand. When we tell 1, it is 30 kilometer. When we tell 2, it is 60 kilometers. Okay. Okay. And when it goes further, you see, when it comes to Neptune and all, its speed is 5 kilometer per second, roughly 5.5. So that was another observation. Okay. Do you know why? Why would that be? Why the planets slow down when they are away from sun? The second law, yeah, tell me. Yes. Hilal, you are talking?
No, sir. You can continue.
Okay. Now you can answer, no problem.
Like the distance between the sun and the planet, like it's when it increases, the speed decrease, the orbital speed decrease.
Yeah, that's what we see. Why it is? Why would that be?
Maybe the length of the orbital.
Yeah, but then the speed should not change, right? It will take more time. The period will increase because of the length increase. Speed cannot change, right? That is why the T squared by R cubed. I asked you, all of you, to go home. It's a simple mathematical expression. If A square divided by B cubed is constant, what does it mean? You know? So that means that the change in A is different from the change in B. Okay, so that is what you should understand from that. Okay, so when T squared by R cubed is a constant, that means T has to be higher. T has to increase disproportionately compared to R. So the period of rotation, that is the time period it takes, is more, which means it slows down. Okay, so this is actually Newton came forward and he put together an equation for this. How this is coming from, which you can also find out. I told in the last class. So now this brings to an important point. I will take you to the whiteboard. So here, like we have to understand now. Let us assume that this is the sun. Okay, and let us assume now this is the orbital path. Okay, of maybe an X planet. Okay, so if let us say there is a small planet here, there are two movements for these planets. There are two motions for these planets. Two motion in the sense, like if this is Earth and if this is the sun, let us assume that this is the sun and this is the Earth. Okay, let's assume this is the Earth. The two motions in the sense, it is not like the rotation on its own axis in the revolution. It is not that. In this revolving around the sun itself, there are two motions. Do you know which are they? Actually, the orbital path is formed and the Earth is rotating around the sun as a combined effect of those two motions. Two tendencies of motion.
Centripetal motion.
Okay. So what is centripetal motion? What is meant by centripetal motion? In the last class, I think Aksa or I think somebody answered. What is centripetal motion? You can even type in chat.
The force to the center.
Yeah, the force to the center. Yeah. Okay. So centripetal motion means a force which is towards the center. So this is called centripetal force. What is that force here in this case of Sun and Earth?
Gravitation.
It is the gravitational force, right? Centripetal force is the gravitational force. So actually, if you equate, that is what Newton did. So centripetal force has an equation called mv squared by r. You might have learned that. Centripetal force is mv squared by r. And in this case, it is equal to gravity. Gravity is g into m divided by r square. So if you equate those two, you can go home and do that. That's your assignment today. You can equate centripetal force equal to gravity. Attempt this. Centripetal force is equal to gravitational force. Okay, centripetal force is mv squared by r. A gravitational force, as you know, g into m1 into m2 divided by r square. Okay, and this mv squared by r, m is the mass of this object, and from that you attempt. From that, actually, Newton derived and showed that t squared by r cubed is a constant. This is why t squared by r cubed is a constant. Okay, that's good. Fine. So this is one motion. What is the second motion? If this was the only motion, Earth would have gone and hit the sun. We talked about that. It's not happening. Why? I think in the last class, one person who did that? He told a very beautiful answer. That. Let me check who told that. Was it Dennis? No, Alvin. Alvin, can you unmute?
Yes, sir.
You only told this, right? Last class?
This one, sir.
Yeah. You tell that now. You explain. Okay. I think, anyway, I think Alvin told, if I am right, if I remember it right, it was Alvin. He told an important thing. He told that Earth was born rotating. Right? So Earth was born rotating. So you have to understand that before the sun, Earth comes into the sun's gravitational field, Earth would have been moving in its own way of motion. Let us say straight line motion. Earth has straight line motion like this. Okay. It is something which is going, and the gravitational field of sun attracts it. So what happens? You have one force which goes here, and one force, not a force, okay, one movement which is directed towards here, one motion, and another motion which directs towards the center. As a result of that, this moves in a direction, in a direction which is along with this orbital path which we have mentioned, which moves in such a direction. So now this moves like this then. At this point, again, there are two forces. The force which we know, the centripetal force, which is constant. From this point also, sun attracts this. And from this point also, the tendency of the Earth is to again go to its original motion. And then as a result of these two, you have it is following whatever orbital path it is having. It goes to the center. So this is how that orbital path is formed. So it is an equilibrium between those two motions. And when that equilibrium fails, let us assume that the sun's gravity increases, which means what will happen? What will happen if the gravity of sun increases? In this case, let us assume some other planet or some other star goes and hits sun, and sun's mass increases and sun's gravity increases because of that. What will happen to Earth?
Earth will be pulled into the sun.
Earth will be pulled into the sun because this force will increase, right? See, as of now, it's a balance between this gravitational force and the straight line motion. That will change. Okay, and now let us assume that Earth is what is happening in the sun is burning of hydrogen to helium. At one point, the hydrogen is getting reduced, right, day by day. So actually speaking, the gravity force of sun will reduce after some point. Then what will happen?
Then the sun will move away from the Earth.
Come again?
The sun will move away from the Earth.
Sun may not move away, Earth will move away because the sun is much heavier than the Earth. Yeah. So when you are sitting in the class in Kuwait, you keep your hands held on to your table, okay? Hydrogen is burning to helium in sun. Any point Earth will move away. Do you fear that? In Kuwait, you may fall apart. Any of you fear? Why it is not happening? Any of you? Why it is not happening? It will happen one day. Okay? As of now, compared to the mass of the sun, the hydrogen which is being burned is a very minuscule quantity, but probably in thousands of millions of years it might happen. So all of you can be relaxed that in our lifetime it is not going to happen. Probably in your child and children's child, your grandson's time also it is not going to happen. So that is a relief which we have. Okay. So this is actually the basic principle of motion. So this was an understanding, and the equations deriving this was brought by Newton. Okay? That is his greatness. And with this actually, that is why we are able to send satellites. When we send a satellite, it's actually by that calculation called T squared by R cubed. Because we know that moon is rotating the earth. And we know the time period moon takes, it is 28 days. We know the distance from earth to moon. So we know the T squared by R cubed of the moon. And as a satellite is concerned, we know, you know how much time a satellite takes to rotate earth? How much time satellite takes for one orbital round completion?
40.
Axa told 90 minutes. Okay. Anyone else? What is the time period? Period of rotation for one satellite. For that, let me ask you, are all the satellites traveling at same speed, or are they running at different speeds? 1 hour, Sri Hari. Okay. Okay. So you have to understand that satellites normally are broadly classified into two. Okay. One set of satellite is something which we are doing for our purpose. It is like a balloon which you buy from the market and tie it on top of your house, on your flat. You want that balloon in your flat. You don't want to give it to somebody else. Okay. Or you tie the balloon to your car or cycle. So whatever is the speed of the cycle, speed of the balloon is the same. Okay. So that is what we call a geosynchronous satellite. Have you heard about the term called geosynchronous or geostationary? Let me type this. Geostationary satellite. Okay. So this means it is stationary compared to geo. Geo is Earth. So why are we sending such satellites? It is mostly for communication purposes, for weather forecast, things like that. So if Kuwait is deploying a satellite, Kuwait wants that satellite to be on the top of Kuwait. So the time period of Earth one rotation is 24 hours. So the time period of rotation of geosynchronous or geostationary satellite is also 24 hours. Because then only the satellite which India is sending will be on top of India, which Kuwait is deploying will be on the top of Kuwait. Now there is another kind of satellite. It's called polar satellites. So that is for a different purpose. Like it is not that we just want to manage our business. We want to know what is happening in other countries. It is like a drone which we deploy to see what is happening in the other houses, right? The spying and all those things. So America wants to deploy probably a satellite to know what is happening in India and tomorrow what is happening in China, kind of stuff. Or maybe they want to study what is happening in the entire Earth. So that is a different one. So the time period of rotation for geostationary satellite is 24 hours. See, so we know the T. So from that, we can find out what should be the distance from Earth to that satellite, which means its orbital radius. That is how it is calculated. If you want, you can go and attempt at your house. Okay. Let me now go back to my previous slide and ask you this. Are you able to see this?
Yes, sir.
Okay, let us assume this guy who is pushing this civic, it is A, and the guy who is lifting this half sleeve guy is B. Which needs more power, A or B? Let us assume this is A. Let us assume this is A and this is B. Okay, this is B. Which needs more power? B, axa tells B. A needs more power or B needs more power? Whether pushing a car needs more power or lifting it needs more power. B. Anyone thinks it is not B? Okay, everybody B. Unanimously, Kuwait votes for B. Okay, why? Why is it B? Why not A? Same car. Let us assume it's the same car. Okay. So this looks like two different cars, but forget about that. Assume it is same car. Why it is B? Come on, it's a very simple question. This is something you study in high school, right?
Sir, in D we have to lift the weight of the car, but in A we have to only pull the car, and there is not much force acting against the motion.
Excellent. So let us come. Was that axa?
Yes, sir.
Okay. So in the case of A, which is the force you have to overcome to push a car? Push a stationary car?
Friction.
Friction. Okay. And for lifting the car?
It's weight.
It's the weight. Okay. Is it only friction? Okay. Let me ask you this question. If the car was running, is it easier to push it? Is it easier to push a running car compared to a stationary car? Is it easier to push a running car compared to a stationary car? Whether it is car or cycle or something.
Yes.
Yeah. Friction should be same, right? In both cases.
It has the engine power also, no, to push that thing.
Do you think it is a engine is off?
Engines off. Then how will it run?
No, it's not running here. You haven't you started the cars which the engine is not.
The brake is removed.
Yeah, that is right. Let us assume you are pushing a car in which the engine is off. That is what we normally do to push start, right? So pushing, is it tough? Is it not tougher when it is stationary compared to when it is moving? Yeah. Why is it so? It is because of friction. Friction is same in both cases, right?
Yes.
Come on, yeah. This is you have to answer this. This is a high school stuff. You have studied this. Okay, let us assume it is kept neutral, Gauri. What is the force that prevents you from moving something which is stationary? Guys, that is called inertia. Yeah. This is what is called force of inertia. Right? You might have probably forgotten it, or it would not have striken to you. You know it. Okay. So the difference is, in the case of A, you are acting against inertia, but yeah, first law of motion. Yeah. Problem, Hilal, is all those laws are there in textbooks and exam answer papers, and it has to be in your mind. Okay. So that is why we are doing this. Okay. No problem. It happens sometimes. Okay. No issues. So now, in the case of this second case, you are lifting something. Okay, fine. So when you are lifting something, you are lifting against the force of gravity. Okay, you know what is the force of gravity, right? Let us assume this is the car. What is the force of gravity here? How do you calculate? It is the mass of the car into the gravitational acceleration. So in the second case, here this person has to act against a force called m into g. M is the mass of the car, g is the gravitational acceleration. So he has to lift it against that. Okay, and that is actually your weight. How do you think the weighing machine operates? When you go to a weighing machine?
It doesn't have actually.
Again, tell me. Repeat.
It doesn't show the actual weight of us. It like some error, like there's a difference between the weight which we are in Earth and when we look in the weighing machine.
Okay. Okay. So the thing is, weight and mass are two different things. Weight is a force. Weight is this mg. So the weight of Aditya is his mass into 9.81 something. That is his weight. Weight of Axa is her weight, her mass into the gravitational acceleration. So if somebody has to lift Aditya, they have to apply force to overcome this m into g. Mass is nothing to do with the force. Mass is actually a physical property. How much of the property you contain? How much of property you contain? Actually, in a weighing machine, there is no system to measure how much of property you contain. So actually, it measures the weight and then divides by the gravitational acceleration, or g. So you first find out mg, and then you divide it by g, then you get the mass. Okay, so weight and mass are two different things. You don't understand that, right? Okay, so let us clear and move on. So this was the finding what Newton did, right? This is something you have learned, like gravity is a universal force. Gravity is an attractive force. Force is proportional to mass of attracting bodies. You have learned all those things, right? Okay. Force is inversely proportional to the square of distance. This is something which you know, right? There's nothing for you to study here, right? All of you know this, right? F is equal to g into m1 m2 by t square, right? Okay. So now what happens? We told about the weight, right? So this is the weight differs. So what is weight? Weight is m into g, right? So there that gravitational acceleration comes, that g part, the gravitational force comes into picture. Okay. So whatever we tell as weight is actually the gravitational force, m into g. And as it is a force, you have this other factors in this, right? When it is in Earth, in that equation, you have g into m1. Like in the Earth, let us assume a stone is falling down. What is the gravitational force on that stone? G, which is gravitational constant, into mass of the Earth, into mass of this stone, right? So when you go to sun, what happens? The mass of sun is very high, so the weight will increase. So weight, your own weight will be very high if you go to sun. Not your mass. Mass is constant. Mass is a physical parameter. What is your size is depending on that. And when you go to some other planets which are less heavier than Earth, your weight will reduce. You see here, if you go to Mars, it is 37 kg. In the Moon, it is almost 1/6. Yeah. Okay. Now you look at this. If this gentleman would have lifted her in some Jupiter or something, his back would have broken. And okay, if it would have happened in a Moon, he could have probably lifted her on the top, like WWF wrestler, right? Weight would have been 1/6. Okay. So if you want to lift your fiancée somewhere, gentlemen and ladies, you better go to some Moon or somewhere and lift them, right? So let me ask this question to you. Give me a problem. Give you a problem. Let us assume you are lifting your fiancée. Okay. I am giving you 3 cases. Okay. Lifting your fiancée. 3 cases. Case number 1. You are, I am clearing this. Whatever you want to note here or take screenshot, you can do. I am clearing this. One case is you are lifting a person by sitting in Kuwait. You are in Kuwait, right? So case A, let me tell, you are in Kuwait, okay, in your home, and you are lifting a person. So that is case number 1, case number A. Case number B is you are lifting the person. The person is, you are going to Mount Everest, say, which is around roughly 9 kilometer height. Okay. So on the top of the Mount Everest, you are lifting the same person on top of Mount Everest, which is roughly 9 kilometer height. 9 kilometer height. Okay. Now the third case, you are going to KGF. You know KGF, right? You have seen that movie, right? Kolar Goldfields, which is roughly 3 kilometer depth, right? Which is a 3 kilometer. It's a mine, right? So you are going below the earth. So in KGF, which is 3 kilometer below earth, okay, where would the weight be higher and where would it be lesser? You are lifting a person, so case number A here on in the earth, case number B on top of a mountain which is 9 kilometer height, case number C in a mine which is below the earth, roughly 3 kilometer. In which case it will be easy to lift the person? In which case it would be heavier? Think about it and answer. So Aksa, you to tell the order. So Aditya tells higher at B, weight is higher at B and lower at C. Okay. CAB in the order of higher to lower, CAB in the order of higher to lower. Okay. So C is the highest as per her. As per Gauri, C will be the higher. Okay. As per Aditya, higher at B. Okay. Others. Where will it be higher? Think about it. Take a pause. Okay. Okay, now let us go. Alvin tells me, let us go a bit deeper into this. Okay. You studied like what is gravitational force, right? What is gravitational force? G is equal to, let us assume the mass of the earth is m. Mass of the earth is m. Okay. Let us assume the mass of this whomever person whom we are lifting is small m. Okay. Divided by r square. Okay. R square. So this would be the gravitational force in the case of A, right? So what will be the gravitational force in the case of B? This all of you know. This is the gravitational force for any object of mass m which is on earth. This is the gravitational force. The case number A is like that. In the case of B, what would be the gravitational force? What is the difference? Anyone? Can you unmute it?
Proportional to the productive masses of two objects.
Yeah, but that masses are not changing, na?
Sir, it
Same.
would be G.
Yeah.
G mm by R plus 9 the whole square.
Or 1 second. Let me tell. In the second case, let us call this FA. Let us call this FB. Tell me. G.
Mm by R plus 9 the whole square.
Excellent. So what is this R?
Radius of the earth.
R is the radius of the earth. Very good. Excellent. Okay. So now this is one point you have to understand. So the gravitational force is something when you tell the radius or the distance is calculated from the center. Okay. So if this is the center of the earth, this distance, which we call as R, is what is the R in the first case. So that is very important, because if the distance was being measured from the surface, then this would have been a very different case. When if two objects have been kept touching each other, then the distance between them will become 0. When the denominator is 0, this force would have been infinite, right? So this is a very important aspect, that when we talk about gravity, the force is centralized on the center of the object, which is what Aksa told. So this is the R. So in the second case, as she rightly mentioned, yeah, you mentioned now, you told R plus 9, right?
Yes, sir.
R plus 9. R is roughly, I think, 6,800, 6,900 kilometers. Okay, roughly. Radius of the Earth. This whole square, right? So this value will be more than A or B, Aditya?
It will be more, sir.
Are
It will
you
be less,
sure?
sorry. It will be less, it will be less.
Okay. All of you, do you agree that B
Yes,
will be
sir.
lesser? Yeah, it is very simple logical. So you come out from these equations. You come out from the mode of the equation. If you keep two magnets, these two magnets will attract, right? And you know that the force of attraction is inversely proportional to the distance between this magnet, right? So if you increase the distance, what happens? The attraction will reduce, no? It's a simple logic. So this is like a magnetic attraction between the Earth and another object. So the closer they are, the attraction will be more. And when the object is very far, like at a height from the Earth, obviously the distance increases and the attraction would be less. That is why the square of the distance is in the denominator. So we understood that B would be obviously lower than A. Now let us come to the C. Anyone? What would be C? Force in the case of...
divided by R minus 3 the whole square.
Okay, so that is where there is a small issue. Okay, so there is another stuff called shelf theorem. I don't know whether you have studied that. It's called shelf theorem. Okay, that's very important. You think about it. Let us assume we are making a hole in the Earth. Okay, we make a hole like a mine. If it go closer and closer and go to the center of the Earth, exact center of the Earth, what would be the gravitational force on us?
0.
Yeah, why is it?
Because it's pulled to the center. When we are already in the center, there is no pulling force.
Ah, brilliant. Okay, so what does it mean? That means that the you'd understand gravity is a function of the mass. When the mass increases is when gravity increases. So when an object goes down, if you take a rock or a soil, if that soil is in say at a specific point like here, let us assume some rock is at this point, the force on this is only by the mass which is within this radius, not the entire radius. Okay, and so when this goes down, whenever this is at some other different point, let us assume it is here, the gravity of Earth which is acting on this mass is not of this entire gravity. It is only by this portion which is in this radius. That is why when it goes to the center, gravity becomes 0. Right? So which means here there is a slight tricky stuff. G is same, but Earth mass is not m here in this case, because this is at a 3 kilometer lower distance. Okay, what is the mass of a sphere? What is the volume of a sphere? How do you calculate mass of a sphere, spherical object? How do you calculate mass of a spherical object? Anyone? We want to calculate mass of Earth. Yeah, 4 by 3 pi r cube, as Alina Santosh mentioned, is the volume, right? Okay, how do you get mass from volume? You should know this. You
Volume
have
into density.
Yeah, it's a volume and density. This is something, it's a high school physics, right? Okay, and density of Earth is, we can take it as reasonably constant. Okay, so here this m would change. This m would change to 4 by 3. So see, this whiteboard is not the best place to write equations. Okay, so you have to understand that. So it won't be the great way of writing it. Into 4 by 3 pi into
R cube.
which r?
The radius of the Earth.
R minus 3.
Yeah, it is r minus 3. So this is what you have to understand. Let us assume this is at the 3 kilometer distance here. This stuff is the 3 kilometer distance, the mine which we are talking about. Then it is a distance between this and the center of the earth. That means the radius from here to this point is what matters in this case, right? So here you have to understand it is the r minus 3 all cubed. Okay, this all cubed, 4 by 3 pi r cubed into the density, let us take d, into the small m, oops, into this small m. Now then divided by what? Divided by what?
R minus 3 the whole square.
R minus 3 the whole square. Whole square. Right? What would happen here? There is one r minus 3 all cubed on top, one r minus 3 all cubed on bottom, right? Both these will get cancelled each other, and one r minus 3 will be on top, right? This r minus 3 squared, r minus 3 cubed on top, so you will have only one r minus 3 on the top, right? So if we assume that instead of this r minus 3 you want to call this by r1 for simplicity, which is the r1 is this distance. This distance, if you assume it is r1, what will happen to this equation? Oops. I'm struggling to get this. Okay, so what will happen to this equation? This one will change to g into 4 by 3 into pi. If this is the equation for this force, right? If this is the equation for force, r1 is lesser than r, right? r1 is lesser than r, right? So this r is coming on the top, r1 is lesser than r. So when r1 becomes lesser and lesser and lesser, what happens? The force reduces as the radius reduces, because the r comes to the top here. Yeah, r is on the top here, that m goes away, r is on the top here. Before this distance, this r and the other distance was in the denominator. Now r comes on the top, denominator it comes. Okay, so because of that, whenever this r is the higher maximum, this force is higher, and r reduces, it becomes r1 and r2, and that becomes 0, this force becomes 0. And when the r1 is equal to r, then it becomes the entire volume of the earth. So the mass is higher, gravity is higher. So gravity is higher on the surface of the earth, and when r reduces to r1 or r2, whatever it is, the gravitational force reduces. The answer here is B has the maximum gravitational pull, A has lesser. Between A and C you have to calculate based on the figure, but the point is, when you go deep on the earth, the gravitational force reduces, and that is very important. It's extremely important, otherwise there would have been a disproportional pull from the center. You understand? You want to ask anything, you can ask, or if you want to go home and work it out, you can work it out. Writing equations in this platform is pretty difficult. But not, you cannot, or I am moving away. Any questions? So this is called shell theorem. Okay, this is also derived by Newton. It's called shell theorem. That the theorem that the gravity which applies on a spherical object, it's very important, is only for the mass which is within that object, that sphere, that radius. Okay. Fine. Moving on. Let us go back to Remy, Tommy, and Shahrukh Khan. So the point is, whenever you want to lift somebody, think where you are standing. Okay, invite for a moon trip or somewhere and then lift. Okay, why? Good. Now, let us get back to the question which I asked in the last class. So I asked this, like you are in a train, you are putting a ball to the top, what happens? Many of you came to the my forum, the GrainEd forum. I'll show you. Are you able to see this? Anyone? Can you see this GrainEd discussion forum? Okay. So yes, so very few people have answered. Suman was the first one to answer. So I was telling it was like typical examinations, right? Till yesterday evening there was only one person who was answering, and then all in a sudden I think you remembered that today is the next class. All of you started coming and answering it. So this forum is to like for us to discuss. It is not that I know all the answers. You can actually interact among yourself also. So whatever I am asking today, I suggest that you come here and you post your answers. You can see others' answer. When somebody else has already answered, don't give the same answer. Then you can see whether you want to add anything on top of it, right? Okay. So now onwards, today onwards, all the assignments come to the GrainEd discussion forum. You know which is your session. You can create a new thread. Not necessary that in this thread. You can create a new thread and answer. You can ask for doubts. If I don't know it, I will refer and I will try to tell something. If you have found out something new, you can share that with me. So this is how we will collaboratively learn. It can happen even after this class. It applies to all GrainEd classes. Okay. So now this is how Galileo looked at it. See, I told you like he was in house arrest during the fag end of his life, and it was near a sea. So he used to have all his experiments, motion experiments he was doing at that time. This is an inclined plane which he made. Like contrary to the story of the Pisa Tower, he going and putting something. This is actually was the inclined plane which Galileo made. And this is how the fundamentals of inertia concept he developed. So he had marbles of different weight. He started putting them here, on top here. And then here in the down, he'll keep a water bowl. And you'll see this one will come and fall in that bowl and how much water spills over. That is a measure of the speed. You know, they did not have that accurate measurement system. So this is how they used to manage. And he was putting different weight marbles, and to his observation that all are taking the same time. Like this is the problem which we told in the first class. That is from, he started developing the concepts of motion, concepts of inertia and all those things. Then this was the next point which he had, that he was thinking like if a boat, like not the motorized boat and all, if going like this, a person standing on this anchoring stuff, if he drops a coin down, by the time the coin falls down, the boat is moved. The new position of the boat is here. The person is here. Will the coin fall on the boat or it will fall on the sea? That was the question. If this person drops a coin from a boat which is moving, by the time the coin falls down, the boat is here. And will the coin fall in the boat or on the ocean because this is moved? Answers please. Will the coin fall on the water or it will fall on the boat itself? This is very similar to the assignment they gave on the boat. Okay, so I think all of you have a very reasonable idea about, Dennis is telling depending on the force it released. Yeah, okay, slightly yes, depending on the direction of force also. But otherwise, if you're just dropping it, it falls on the board. Why is it that all of you have come, most of you have come and answered in the assignment that the person travels in the boat say at the same speed as the boat. See, otherwise you think about it. When a flight takes over, you know that Earth has a speed, right, roughly 1,600 km per hour, and flight normally travels at 800 or 1,000 km per hour. So when you know the Earth is rotating in one direction, when a flight takes off, actually, if this phenomenon was not there, the flight would have landed on the other side. Because by the time Earth has moved. So when a flight takes off, the speed of the flight is equal to the speed of the earth or speed of the place where from it started. Okay, so we will ask a small problem. Please read this. Answer, please. A train, a normal train, which is traveling at 50 km/h. A person inside the train is walking inside the train in the same direction of the train, the same direction in which train moves. A person is standing in the field outside watching. What would be the speed of this person who is traveling inside the train for this person who is standing on the field? Hilal says 50. See, read it again, okay? Read it again. Read it again. A person is traveling in a train. Train is traveling at 50 km/h. The person inside the train is walking inside the train at 5 km/h speed in the same direction of the train. So what would be that person's speed for an observer standing outside? 50, 50, 50, 55. 3 votes for 50, 1 vote for 55. Aditya likes speed, so he increased it. Alvin also likes speed, 55. 55. Oops, all of a sudden the votes are changing to 55 now. The 50 guys, you have a chance to correct. You want to change or you want to stick on to 50 and fight out with these guys? Okay, okay. I want one of you to unmute. Alina Santosh, can you unmute and talk?
Yes, sir.
Yeah. Why is it so?
So because it's in the same direction.
Okay. It's in the same direction. So
it's added.
Okay, added.
And so like the person who is seeing outside is seeing the speed of the train. So
Okay. It might?
Will be 55, like the speed of the person, because since he's going in the same direction itself, so it will be the speed will be gone along with the speed of the train. So we will add it, right?
Yeah, you will add it. I agree to you. Dennis, so you have to understand this concept. Okay, Dennis, you understand this concept. So there is nothing called constant speed is what we are getting to know. What would be the speed of this person who is walking at 5 km/h for another person who is sitting in the train? For a person who is sitting inside the train, what would be the speed of this person who is walking at 5 km/h? It is 5, right? It is 5 km/h. You think about it. You are in a train, one person is walking at 5 km/h. So for you, that person is walking at 5 km/h. But for a person who is standing outside, that is not so. Because for a person who is standing outside, even a person who is sitting inside a train is traveling at a speed of 50 km/h. So when you add another 5 km, it becomes 55. So what does that mean? That means there is nothing called constant speed. It is depending on from the place where from you are observing. Okay, we tell a name for that in science, for the place where from we are observing. Depending on the place where from we are observing, the speed will change. In science, we call it as frame of reference, not this name. You can take a note of it. It's important terminology in case you are studying science in future. It is called frame of reference. So here we talked about one frame of reference is the place outside the train, and one frame of reference is the train itself. So from the frame of reference of train, this person is walking at 5 km/h, and from the frame of reference of outside the train, it is 55. And what from this frame of reference? What is the speed of the same person from another frame of reference, from another train which is going in parallel track at 60 km/h in the same direction? So for a person who is sitting in this new train, when that person is watching the other person who is walking in the other train, which are going in parallel tracks, what would be the speed? So two trains, in one train going at 50 km/h, a person inside the train walking at 5 km/h, another train in the parallel track going at 60 km/h in the same direction. So for a person who is sitting in the 60 km/h train, what would be the speed of the person in the other train walking at 5 km/h? 5 in which direction? 5 in which direction? Yeah, it's actually -5. For a person who is sitting in the 60 km/h train, it is -5. Or like what you tell 5 is right. The person will feel like this person is going backward in 5 km/h speed, right? Let us assume that person is not walking. Some people are sitting in that train, 50 km/h train. What would be the speed when you look from a 60 km/h train? It would be 10 km/h negative, going backwards, right? Okay, what would be another train in the parallel track going at 60 km/h, but this time both the trains are in opposite direction. So from this train, when you watch, what would be the speed of that person who is walking? Axa, you have to think about it. Two trains, one train going in one direction at 50 km/h, a person walking at 5 km/h in same direction. Case number 3, the train in the parallel track is going at 60 km/h in opposite direction. So when you look from that train, what would be the speed of the person? See, you cannot give to me like, okay, I tell this is wrong, you tell one answer, okay? You have to be convinced. How is it coming so? 5, 115, 65. Kuwait seems to be in splits. 115. More answers. I think some people are waiting to see in which side there is majority. And put. I think with the logic which you answered 1 and 2, this is same logic, right? You travel in a car. When you look at the trees outside, you feel the tree is going backside. This is the same phenomena. But in this case, the trees are actually going backwards, right? So in this case, actually 60 km on one side, 55 on another side. So it is 60 plus 55, 115 is the speed difference. And as Suman has mentioned, it is going in opposite direction. So this is basic relativity of motion. Okay, this is not Einstein's relativity. This is basic relativity of motion. Einstein's relativity is a bit different. It's a bit more complicated. We'll come to that. I'll give you an assignment. You can note this down. This is your assignment for the day. You can take a screenshot or note down. Don't do it now. It has a bit more efforts. You can do it easily. Okay. Second the question. Ponder about it. We will discuss it in our GrainEd.com. Okay. So escalator speed is constant. Person's speed is constant. From that you try to figure out. We will discuss in the coming days. You know, you can post your answers. Nothing wrong. You try out. When you try many times, you know, we will get it right. Fine. And this would be the kind of questions which normally you face in competitive exams and all those things. So unless you have a theoretical understanding about this, it's very difficult to, you know, crack this kind of problems. Fine. So now you have the theoretical understanding of relative motion. So it should be easy for you. Okay. Now we saw this, right? We discussed about this in the last class. We discussed this, right? About what would be the impact in this case. Like we told, like if a person is catching a cricket ball or a football, you take it back. Actually, you're taking it back so that you increase the time, and that's because of which the force can be reduced, right? we talked about in the last class. One of you please open and tell. We covered this in the last class, right? Some of you answered also, right? Aditya, did you? Did we?
Yes, sir.
Okay, so we covered. Okay, so here, like in this case, we know if the mass of this truck is more, or mass of this car is more, the impact is heavy because the force is mass into acceleration. But there is a method to reduce the impact. Let us assume this car had a big bumper in front and the truck does not hit at once. It slowly, the speed of the truck, let us assume it was 100 km/h. It comes to zero in probably 10 seconds instead of 1 second. Then the impact on this car would be pretty less, right? Same case here. If somebody hits on your face, you suddenly pull it back, then you get some time for that force to get applied. So what happens? Force we know is mass into acceleration. Acceleration is depending on, it is the rate of change of speed. So when that time increases, rate of change of speed reduces, force reduces. So that we learned in last class. Okay, right. So now actually from this is where actually basic equations of what you call as the kinematics you derive, right? Let us assume like you have some object, okay? So you know that let us assume it is having some velocity u, right? And you come and apply, somebody comes and just pulls this, just pushes this with some force. Some force we apply here and pushes that ball. And the speed obviously will increase, and ball after some point reaches this position. And let us assume when it reaches this position, its speed becomes v. Okay? And if the time taken for this is t, what is the acceleration here? If the time taken for this is t, what is the acceleration here? A ball which was going at some speed u, somebody comes and pushes it, and because you push, its speed increases to v, and that happens in t period of time. What is the acceleration here? Yeah, v minus u. Yeah, actually when you do like that, you have to put a bracket to v and u, otherwise it will read as v minus u by t. But I know you know it. Okay, good, no problem. So all of you know this. So what is, so this comes from the definition of acceleration. So this is what you have to understand. What is acceleration we told? Okay, so this is what Newton brought a theoretical like explanations to it. So he told, like we told about the car and truck hitting each other, right? Okay, so listen to this carefully. So we know that if the mass of the truck was heavy, instead of the truck, if a cycle would have come and hit you, the impact would have been much lesser. The force would have been much lesser. So we know that the mass of the object is playing a big part. Similarly, the truck could have come very slow at 5 km/h and come and hit you. The impact would have been much lesser. So you know that when the speed is more, again the impact is high. The same cricket ball, when it comes at a heavier pace, when you try to block it, you have to apply more force. So you understood? Two parameters are determining the force. One, as we understood, is the mass. Mass is determining force. So we understood that force is proportional to mass. Is proportional to mass. Let me put, I don't get a symbol here, okay? Just read it as proportional, okay? And then we understand that the speed also is proportional to mass. So we got two parameters. Speed is velocity. The velocity is also proportional to mass, okay? So Newton came forward by telling that force is required to change the speed of any object. Force is required to change the speed of any object. So that is a change from Aristotle to Newton. We mentioned that either to reduce its speed or to increase its speed. Okay, so that's what he mentioned. But then mass is an important parameter. When mass is more, you have to apply more force. So he came forward with this explanation that actually then that force is what is the change in mass and velocity. So mass and velocity put together is one thing. You know what we call it as?
Momentum.
Yeah, that is what we call it as momentum. So this impact, like like when a car comes and hits or truck comes and hits, its mass is more, impact is more, speed is more, impact is more. To decide to describe that phenomenon, we told, okay, let us use this name called momentum. So momentum is a combined effect of mass and velocity. So Newton's definition was force is actually something which is needed to change the momentum. So he brought up a term called, that is force is rate of change of momentum. So this word called rate of change is an important word. So that actually means the change over a time. Let us assume momentum was m1. After some point momentum is m2. Rate of change is m2 minus m1. That is the change in momentum divided by the time. It is just like acceleration. Okay. So this is where from the fundamental equation comes, by telling that momentum is mv, and what is the change in mv over a period of time. Change in momentum over a period of time, and we know v by t. Change, v is the change, right? So change in momentum, like let us assume at this point the momentum at this point is mv. When we started, the momentum was m into u. So mv minus mu by t. So that is the basic simple equation Newton defined. That is, the force is required to change the momentum. So momentum here was mass into velocity, m into u. Momentum here is m into v. So change in momentum is mv minus mu over a t time. So that is rate of change of momentum. And as you know, you can take the m out from here. So it becomes m into v minus u divided by t. And as many of you told, this v minus u divided by t, that is rate of change of speed or velocity, is what we call as acceleration, right? So this is where from the f is equal to ma comes. So that is from observations of people over 1,000, 2,000, 3,000 years that he could build, and on the foundations built by many scientists and philosophers over a period. It's not like one fine day an apple falls down and he gets a dream that f is equal to ma. It is not like that. Okay, so you understood that from here you all told a is equal to v minus u divided by t. Okay, when you write like this, all of you have to put that bracket, otherwise it will read as v minus u by t. Okay, so if you resolve this equation, what happens? If you bring the t to this side, it becomes a into t is equal to v minus u. It's simple mathematics, right? And from this, if you bring the u to the other side, you get v is equal to u plus at. Oops. This you have studied, right? I think this is the basic. This actually comes from this basic definition. There is no rocket science here. This actually comes from this basic definition. Okay. Now let me ask you. This is the question to you. Let us assume this distance from here to here is d. What is that d? How do you calculate that d? If this distance is d, how can you calculate that d? Think about it. What would be d? An object had a speed of u. It traveled in a time of t, a distance of d, and its new speed is v. How do you calculate d? How do you calculate distance when you know the speed and time? High school mathematics. Come on.
Distance is equal to speed into time.
Distance is speed into time. It's a high school mathematics, right? What is speed? Speed is the distance which you travel in a unit time. 60 km/h means in 1 hour You travel 60 kilometers. In 5 hours, how much you travel? 5 into 60. Right? So what is the speed here? If you know the speed here, if you multiply with the time, you get this distance. So what is the speed here? Which speed you will take? Starting is u, end is v. Which speed you will take? Anyone? When you have two different speeds, starting speed u, end speed v, which speed you will take to calculate the distance traveled? Anyone? This is the last one. With this we'll finish. No? That is what we call as average speed. But provided it is uniform acceleration. If it is not uniform, like it is running at 60 kilometers per hour for the first 4 hours, and the last hour only it picks up the speed, then it won't be true. Okay. So here we know that the distance traveled d is equal to speed into time, and speed is average speed. Average speed. What is average speed here? Anyone? What is the average speed? Starting speed was u, end speed was v. What is the average speed? Yeah, so you know the average here. Your physics mark is 80, your chemistry mark is 90. What is average? 80 plus 90 by 2. This is all simple high school mathematics, right? We are just applying that in physics or probably in some other scientific stuff. Yeah. So the speed is, so you know, it is u plus v divided by 2 into time, right? Okay. So from this, we know v is equal to u plus at from here. So if you substitute that, v is equal to u plus at divided by 2 into t. Okay. So what happens? U plus u is 2u, right? And you have an 80 divided by 2 into t, right? So now you expand here, this becomes 2u by 2 is u plus at by 2, at divided by 2 into t. Don't forget the bracket at any point like this. So from this, you will get, when you multiply this t, when you open the bracket, it becomes ut plus 1 by 2, 80 into 2, t is 80 square. This you have studied, right? This is how that comes. This is a very simple derivation which you can do. So why I am telling this derivation of it? This is for you to know that this is such a simple thing. So if you by heart s is equal to ut plus half at square, you may not even know where from it is coming. And this is something which you know very well with the high school mathematics which you studied. From the simple understanding of motion, you can derive this. If you want to note it down, you can note. Otherwise, I am opening for questions and answers. Shall I switch from the screen to take screenshot or something you can take?
Just a second, sir.
Yeah. Either you want to write, you can write, or screenshot you want to take, you can take. So there is one more equation for kinematics, right? I think you should derive it in a similar manner. That is a bit longer. It's very simple, very longer. To type here, it's a bit difficult, unlike the boards as I'm not doing it. So you have to understand, like, majority of the laws and theorems and equations which you study is so simple. From the basic understanding and fundamentals, you can derive it. Then you will not forget it, right? Okay. Shall I switch? So you can either take a screenshot or write this. Okay. There are no questions. You can move. You can note the assignments. You can come to GrainEd.com and probably create different thread for different assignments and write the answers. Then we will discuss. There's nothing right or wrong here. We'll figure out.
Good afternoon, Satish sir.
Namaste.
On behalf of Balavedi and PPF, once again we thank you. You have covered the curriculum as well as extra curriculum, practical, and Newton's thoughts at that time. It's great. That's all I can say now. All the children hope got benefited. and please do their assignments, and please come for the next class in time or earlier than the time is given. God bless everybody. Stay safe. Stay home.
Thank you, Joseph, sir.
Thank you.